Hello and welcome to the lecture series on Power Electronic 2 course. In today's lecture we would be seeing how we can classify power electronics. Okay, so power electronics basically can be classified in this way that I have shown here on the board. So we have got the power electronic switches, and then there are power converters, and then there are areas where power electronics is used. Okay, so let's start with the power electronic switches. So by switch I mean the normal switch. Okay, say for example this switch which is normally present at your home, okay, by which you turn on the light or turn off the light, turn on the fan and so on. So this is a normal switch, and you can turn it on and off. Okay, but there is a limit here to the number of times you can turn it on and off in 1 second. Okay, at most you can turn it on and off say 2 times or 3 times in 1 second. So the switch that we'll be talking about in power electronics is a switch we can turn it on and off say thousands of times. So that's the basic difference between an electronic switch and a mechanical switch. So when I am talking about switch, I'll be talking about these fast electronic switches employed by power electronics. Okay, so we will see how we classify the switches that are available in power electronics. So power electronic switches can basically be categorized as uncontrolled switches, then we have semi-controlled switches, and then we have fully controlled switches. Uncontrolled switches include the diode, and you know what is a diode. So we have an anode and a cathode here. So cathode, if the polarity, the voltage here, say this is VC and this is VA, so this diode will be conducting when the voltage at the anode is greater than the voltage at the cathode. So when it is conducting, it is as good as this switch, a mechanical switch, is on. Okay, so it is conducting, and ideally there shouldn't be any voltage drop here. Okay, the V drop should be equal to 0 ideally. But we will see that in a power electronic switch we do have some small drop appearing across the device. Okay, and a better switch is one which has got this drop as low as possible. Okay, but in the analysis that we will be doing in subsequent chapters, we will assume that this drop is ideally equal to 0. Fine. And the second case is when this cathode voltage is greater than the anode voltage, and this is a sub criteria. This is the criteria for on, when the diode is on, and this is the criteria for diode is off. But this is not the only criteria. There is another criteria, that the current that is flowing through the diode, call it anode current, this anode current should be less than which is called the holding current. We will assume that this is equal to 0. So if that becomes the case, then if these two conditions are satisfied, then we say that the diode has turned off. So it will now be in a state wherein the switch is off. Okay, so diode basically is an uncontrolled switch. It turns on when the anode potential becomes greater than the cathode potential, and it turns off when the cathode potential becomes greater than the anode potential, along with the anode current reducing to 0. So this condition is very important. There is a normal misconception that diode will turn off when the cathode voltage has become greater than anode voltage. This is although a necessary condition, but this is not a sufficient condition. Sufficient condition is that the anode current has to drop to 0 for the diode to stop conducting. Okay, so that is why we call diode as uncontrolled device or uncontrolled switch, because turning on the diode or turning off the diode is not in the hands of the user. So it just depends on the circuit condition. Okay, and within this category we have the Diacs also. Diacs are also uncontrolled devices, power electronic devices. We basically won't be taking up the device physics, the characteristics here. I am just classifying the switches, and I will be classifying the power converters in this lecture. Okay, so for the detail about the switch characteristic and switch or the device physics, I would be preparing other lectures. Okay, now comes the semi-controlled switches. Semi-controlled switches, the most famous being SCRs, silicon controlled rectifiers. The silicon controlled rectifiers, which you would already have studied in the previous course of power electronics. Okay, and it comes under the thyristor family. So this is a thyristor. SCR is a thyristor, and we call it a semi-controlled device because, and it is basically symbolically represented like this. So again here this anode, this is your cathode, K or C, whatever you like, and this is another terminal which is also a control terminal, and the current Ig will control the turning on process of the SCR. Okay, so it is called semi-controlled device because we can turn it on when we supply a gate current, sufficient gate current to the device, but we cannot turn it off when we want. Turning off is similar to that of a diode. That means these two conditions, the off conditions, should also hold good for SCR. Okay, so here also Vk, if it becomes greater than Va and Ia, the current IAK, say IAK, it reduces to 0. If these two conditions are satisfied, which are again circuit dependent, then the SCR turns off. So that is why we call SCR as a semi-controlled device, because we can turn it on whenever we want by supplying a gate pulse, gate current, but we can turn it off. It depends on the circuit condition. Fine. So within this thyristor family, we have also got Triac. So we can control the turning on of the SCR in only one quadrant. So again, I won't be going into the detail of the quadrant operation of SCR and Triac. Just for the sake of introduction here, I will be telling you that in Triac we can control it in first as well as the third quadrant. Okay, so that reverse current can also flow through the Triac. So in SCR, current can only flow in one direction through the switch. So if this is SCR, then current can flow only in one direction. Current cannot flow in this direction. But if it is a Triac, okay, if this switch is a Triac, then current can flow in both directions. So that is the basic difference between a Triac and an SCR. Then so these two comes under semi-controlled devices. Now come to fully controlled devices. So fully controlled device include the BJT, and I will be talking about power BJT. Okay, so whenever I will say BJT, it would mean power BJT. Similarly, power MOSFET and IGBT. Okay, then GTO. So these are some of the fully controlled devices available to us in power converter set of devices. And why they are called fully controlled? Because we can turn on and turn off them with the help of the gate signal. Okay, so in case of power BJT, the base current control the turning on and off of the switch. Similarly, in MOSFET, we have gate to drain voltage. If it is on, then switch conducts, if it is 0, and this is a voltage controlled device. Again, these things have got a detailed discussion in some other lecture. Okay, for the time being, just understand that these devices are fully controlled. They can be turned on and off with the wish of the user. Okay, so you have to suitably provide the firing pulses in form of current or in form of voltage, because some of these devices are current controlled, like your SCRs, okay, while some of them are voltage controlled, like your power MOSFET or your IGBT. Okay, BJT is a current control device. So there are some differences between the various devices, but the basic feature of them is that they are fully controlled. Turning on and off is possible. Okay, so this was a brief introduction about the power electronic switches available to us, and these will be used and they will be connected with some other passive circuit elements like inductor and capacitor, and they will form what we call power converters. So let us now look into the various power converters that we use. And power converters, we can again classify them in 4 types. Okay, so the first being your AC to DC converters. Okay, and they are also called rectifiers. The second being DC to DC converters, and they are DC to DC converters, nor we call them choppers also. Okay, if choppers, if it is a buck converter. Then we have AC to DC converters, AC to DC converters, and they are called inverters. Then finally we have AC to AC converters, which are also called AC regulators, or I will come to it. There are other names of this converter also. Okay, so in your previous course on power electronics, which was Power Electronics 1, you studied about the AC to DC converters and AC to AC converters. In this course, Power Electronics 2, we will be taking up these two converters, the DC to DC converter and the AC to okay, sorry, this is not AC to DC, but it is DC to AC. Okay, please correct it. So I had made a mistake here. So this is DC to AC converter, which is called inverter, and these two converters, the DC to DC and DC to AC, will be studying in this course. Okay, so let me focus more on these two converters. So I will erase it. and I will try to classify the DC to DC converters also. Okay, since we have to study it in detail, so I'll be classifying the DC to DC converter in bit detail. So DC to DC converters are classified like this. So basically you can classify it in two major types. The one being your non-isolated DC to DC converters, and the second one is your isolated DC to DC converters. Okay, the non-isolated DC to DC converter include the buck converter and the boost converter, and the third being your buck boost converter. These are the conventional converters which comes under the category of non-isolated converters. Why we call them non-isolated converters? Because the input side and the output side, they are not isolated by way of some transformer. Okay, so that is why they are called non-isolated DC to DC converters. Now, why there is at all a need to isolate the input side and the output side? The basic reason being to have more reliable operation. Okay, to have a magnetic isolation between the input and output side, ensure that the operation is reliable. Okay, and one more thing that you would be wondering, why at all a transformer is required in a DC to DC converter. So how can a DC to DC conversion be there with the help of a transformer? Because transformer is AC to AC conversion. How DC to DC convert, how it will work with a DC to DC converter? So we will I won't be answering this question right now. When I will be taking up each of these converters topology in detail, then I will be explaining you at that time. For the time being, just remember that these form the non-isolated type of DC to DC converters. Okay, apart from them, there are some other converters also, which we call the Cuck converter. These are some famous converters, Cuck, and then Sepic converter is there. Sepic converter. So as the name suggests, buck converter. So what it does, it converts a DC voltage into another DC voltage, a DC voltage, a higher DC voltage into another DC voltage of lesser magnitude. Okay, so higher DC voltage is converted into a lesser DC voltage magnitude with the help of these buck converters. So another question arises, why at all there is a need to convert a DC voltage into another DC voltage? Because I had already told you that in our homes, in industries also, there is a mismatch between the availability of the power source and the load. Okay, so say for example, what are the various DC sources available to us? So DC sources are normally available to us in form of batteries. Say lead acid battery is normally used in homes, so that is a 12 volt battery. Okay, so if we intend to use that battery, 12 volt battery, for charging our mobile which operates on 5 volt, so the battery is 12 volt and the battery of the mobile is 5 volts, so charging has to be say somewhat higher for say 6 volt, but cannot charge a 5 volt battery by directly connecting it to a 12 volt battery. Okay, so that voltage has to be brought down. So that is done with the help of some buck converter, wherein the voltage level is reduced. Then again, there may be case wherein the supply voltage 12 volt is not sufficient to to power a load which requires a higher DC supply. Okay. So in that case, we have to go for the boost converters. So the boost converters, what they do, they convert a lower voltage magnitude, DC magnitude, to a higher level magnitude. Okay. And buck boost, as the name suggests, so this voltage can be converted into a higher, or it can be converted into a lower magnitude voltage. So both things can be achieved with the help of this buck boost converter. But there is a disadvantage with this buck boost converter, is that the output voltage polarity reverses. So we'll talk about it in detail when we're discussing the buck boost converter. This is a disadvantage that is associated with the buck boost converter. The voltage polarity reverses. So in order to overcome that disadvantage, this CUC converter has been introduced. So this converter, CUC converter, is also a buck boost type of converter, which can produce a voltage greater than or less than in magnitude to the input voltage. But the advantage here is that you get the same polarity at the output as what is there at the input. And similarly, SEPIC converter is also a type of buck boost converter. So these are the various non-isolated converters of DC to DC type. Okay. Now coming to the isolated converters. Isolated converters normally employ a high frequency transformer in between the input side and the output side. Okay. So these include the flyback converter. This is the most famous flyback converter. And then we have half bridge, the half bridge, then we have the full bridge converter. Okay. Then we have the push-pull converter, push-pull. So these are some of the topologies of isolated DC to DC converters. And I had, as I had already told you, that the advantage with the isolated DC to DC converter topology is that you get an isolation between the input and magnetic isolation between the input and the output, and this enhances the reliability of the converter. Okay. So this is a broad classification of the various DC to DC converters that we have to study in this course. Okay. So let me move to, now let us move to the application of power electronic converters. Okay. So should I discuss the inverters also? Yes, let me quickly touch that, because we have to study about the inverters also in this course. So inverters are basically DC to AC type of converters. Okay. So we can broadly classify it as line commutated, and this is forced commutated. So what is the difference between a line commutated and a forced commutated inverter? So line commutated inverter are basically rectifiers, AC to DC converters, but they operate in the inversion mode of operation. That is the basic difference between a rectifier and a line commutated inverter. Okay. So the circuit topology remains same. The only difference is that the firing angle alpha is kept higher than 90 degrees, which ensure that the average power is transferred from the DC side to the AC side. There is a bidirectional power flow, but the average power is negative. That means the DC side is feeding the AC side. So basically that is a line commutated inverter. Okay. And the forced commutated inverters they are again be classified as two-level inverter and multi-level inverter. Multi-level inverter. So what is mean by two-level inverter? So we have this DC supply and it is converted into AC. Okay. So just see here. So this is a DC and this is converted into AC. So now AC voltage has got two levels. This is a plus VDC and this is your minus VDC if this is your VDC. Fine. So there are only two levels, plus VDC and minus VDC. So that is why we call it as a two-level inverter. Okay. While a multi-level inverter has got various levels. Okay. So these are the various levels in 1, 2, 3, 4. So 1, 2, 3 and one more will be there. Sorry, yes, one more like this. So this is your multi-level inverter output. So you can easily see that the multi-level inverter output has a better waveform than the two-level inverter, because this resembles a sine wave more closely as compared to this two-level inverter. Okay, is it fine? But definitely the complexity in the circuit increases when we go for multi-level inversion. Okay, so these are basic classification of the inverters. So let me now move to the application of the power electronic converters. So in one of my lecture I had already talked about the application in generation part of the electrical power and the transmission part of the electrical power, and then the third one is your utilization part. Okay. So in generation, nowadays we are moving towards the renewable energy sources of generation, and these renewable energy sources normally have to be the power generated and the voltage level generated by the non-conventional sources like solar PV is DC in nature, that has to be converted into AC, then only it can be fed to the grid. So we require inverters there. Okay. And similarly in case of your wind power generation, so the voltage level that is generated is lesser, we have to enhance it, then we can feed it to the grid. So again converter comes into picture. Similarly in transmission, we have HVDC coming in a big way, high voltage DC transmission, and in HVDC transmission we have rectifier station, we have got inverter station wherein power electronic converters and devices are employed. Similarly in again the facts devices which play a very important role nowadays in AC transmission system, which improves their performance. Okay. So these fact devices basically compose of power electronic devices. Similarly in utilization in industry as well as in home, we find power electronics almost everywhere. In every electrical equipment you take, you will find some power electronic converter or some power electronic device working in it. So it is almost impossible to think of electrical equipment without employing any power converter device. Okay, so just imagine the importance of power converters nowadays in electrical engineering system. Okay, so with this I stop here, and then I will be moving to the DC to DC converters, and I will take up the buck converter and in the subsequent lecture. and we'll discussing all the types of DC to DC converters, the isolated and non-isolated type, and I hope you will like those lectures. Thank you.